Hi, everyone. Thank you so much for joining us today. Welcome to our March webinar, which is all about managing heat-related challenges to railway track. I'm Jackie Jenkin, Marketing Manager here at Senceive. I just have a couple of housekeeping notes for everyone. The first is feel free to type questions into the question box as the webinar goes along. At the end, we're going to host a short Q&A session, and we'll try to get to all questions. The second thing is just to let you know that this webinar is going to be recorded and will be sent to all attendees and registrants after, likely tomorrow, probably. I'd now like to introduce you to our speaker today, Dom Quiche. Dom has worked in instrumentation and monitoring for over 15 years. He's been involved in some of the UK's largest infrastructure schemes. He transitioned to Senceive in 2021 as head of product development, and he has helped us to successfully launch many of our new products, including the digital interface node and Senceive IO. He is also a member of PWI and CICES. So without further ado, over to you, Dom.
Thank you, Jackie. Thank you, everybody, for taking the time out of your day to join this webinar. As I said, my name is Dom Quiche. I'm the product management here at Senceive. So what I want to sort of try and do is set the scene around track buckle, what it is, and in relation to temperature and the challenge that we have. I want to talk about the role that remote monitoring can play in helping to keep railways moving for this particular occurrence, and then finish on some of the challenges that are yet unsolved or need a little bit more thinking around them for us to progress. And as Jackie said at the end, we'll hopefully have time for questions. Apologies for our sort of southern hemisphere attendees today. Obviously, preparing for summer is something that we're very much looking forward to over here in the UK and the Northern Hemisphere. But hopefully there's some nuggets you can pull out for your summer next year. So why do we care about track temperature? Generally, material, when it heats up, it expands, and for a big lump of rail, this is not an exception. And even in the most temporal of climates, there's still a swing of temperature between night and day that has an impact on the linear length of a rail. Like in many structures, we put expansion gaps or joints in place to allow the rail to move in this linear fashion. And this was the normal way of doing things. We called this jointed track. And this is where you have bolt holes at the end of the length of track. You put a plate either side, and you effectively just bolt the two ends of the railway together. However, if you do start to see some decent swings in temperature, you can start to see sort of tens of mil of movement, and the bolt holes start to degrade, and ultimately you start to see a failure, leaving the track unsupported. So a big move was to CWR, which is continuously welded rail. Especially here in the UK, we moved to replace a lot of jointed track with CWR during the 70s and the 80s. And effectively, continuous welded rail comprises of stitching many miles of rail together, fastening into the sleepers. Through these fasteners, we hold them into place. We apply a force to them, a tensile force, in order to keep it in place and keep it nice and rigid. And this has lots of benefits. It's stronger, it's smoother, and allows you to run faster trains over it. However, with CWR comes another headache. What happens when the track expands or contracts beyond its compressive range, you start to see some more issues. The track sits in a tensile stress that actually makes it stronger, allows the rail to hold its shape better. By stitching it together and applying that tension through the rail, we're improving the rigidity of the rail. There's an example in a paper written a few years back about a piece of paper. If you pull a piece of paper apart, it becomes a lot stronger. If you start to push it together, you start to see the paper fold, and that's where the forces that have got nowhere to go and they start to act out. So we don't really stress the rails. In fact, the opposite, we create a stress-free environment where tensioning holds the rail in place, and the rail can act fairly comfortably within these parameters. However, when we exceed these levels and we move into a compressive stress, that compressive stress means there's nowhere for these increased forces to go, and that's where we start to see issues, and they manifest their way in where buckles and kinks. It's important also to point out these are not just unique to CWR. We still get these in jointed track as well, regardless of the fact that we have expansion gaps intended to take that expansion, but generally we see it to a lesser degree. And obviously pretty obvious, but the result of track exceeding its stress-free level is usually a buckle or a kink. These can appear in different wavelengths, different amplitudes, or locations within a high-risk area. It's where these compressive stress become too much for a track to hold. It's that release that we see, and that's what we term as the buckle. And this can be with sleepers or ties, or even shear away from the sleepers or ties. And there's lots of lovely examples there taken straight out of Google Images. So there's lots of sort of contributing factors that can assist in a negative way of track buckle, and they need to be added into the equation, and they're mainly around the track bed and the rigidity of the track bed. Things that need to be considered, like the back of the shoulder. This adds an extra weight and an extra structure to the sleeper and the track, allow for a more stable condition. Track maintenance, has the track been tamped recently, or is there any works being carried out around it that might weaken the track? Is the track area near some points or some turnouts or some switches? By definition, these are supposed to move, and therefore often weak points within a track area. What is the rail actually installed on? Is it concrete ties, timber ties, timber sleepers, or track slab? They all offer different levels of stability and different levels of support. The track slab is by far the most rigid, but to be honest, it's not. It's equally the most expensive. What are the train speeds that you're running over the area? The faster the trains, the more force you're putting through the rail, and potentially disrupting the ballast underneath, creating weaknesses. And if there is a compression within the rail, it will exploit that weakness and start to develop a kink. As we've all sort of figured out, all of these elements focus on the stability of the track bed in order to take that compressive stress if it falls out of the range of what it's been set to. So what causes the increased stress? And obviously the name of this webinar gives it away, but it is an increase in temperature, as I said at the start. The track is set to a range that is suitable to that climate. In the UK, we have an average summer maximum of 27 degrees Celsius, believe it or not. Doesn't feel like it at the moment. And we set something we call in the UK called critical rail temperature on that, which is a temperature that is the maximum before a rail is considered stress. This is also has an allowance for the track conditions that we mentioned in the previous slide. And there's, just not just in the UK, but in lots of rail authorities, there's a fairly developed matrix of managing what that critical rail temperature might be, and considerations that need to be taken in place to get the most accurate number. For example, a well-maintained track might have a critical rail temperature of 59 degrees Celsius. You might say that's the point at which the rail is going to go above its tensile stress and into a compressive stress, and we're in the danger zone. But if the track is on timber sleepers, or it's near some sets of points, or there's some adjacent construction going on, that will rapidly start to decrease, and that number might come near a sort of summer maximum. We also need to consider the fact that air temperature is not the same as rail temperature, and it can be as much as 20 degrees difference in that. So, there are some mitigation that we can try and do to protect the track from rising temperatures. you know, setting the tensile stresses and the track design as a whole is a real balancing act. The obvious question is why don't we just increase the temperature maximum that a rail can suffer before it moves into compression? But let's not forget that we can't increase the range, we just move the range up and down the scale. So if we increase the upper end of that, then we also increase the lower end of that. And in colder conditions comes its own problems. If it's too much tension, you start to get cracks. So if we set that too high, we have more issues in the winter. If we set it too low, we have more buckles in the summer. There's a real balancing that the track designers have to do. The other obvious sort of point that is made is why don't we re-stress the rail seasonally? Obviously, we have different conditions in the winter time through to the summer. And this is actually done in some countries because the swing is so great, but also usually because they have different uses of their rail, potentially different traffic levels. But in most countries, most European countries as well, it's just not practical from you know, thousands of miles of track that need to be have a level of downtime, have to be resourced at the same, you know, we have to go out and do it the same, roughly in the same season each year, and it carries a huge cost. And as we sort of said, it's not just a simple number that you set, you know, track condition and maintenance needs to be taken into account. So suddenly you're having to apply different track designs to different areas. Doing that twice a year suddenly becomes a major undertaking, both technically and commercially. But, you know, one mitigation is to use different grades of steel that have a higher fracture toughness at lower temperatures, which means you can expand the range at the top end. These grades of steel often have inferior things like fatigue or wear resistance, which limit the lifespan of a rail, which means you might end up having to swap them out more regularly. Or you can get ones with heavier cross section. So again, it take bigger loads at a low level, a low temperature, but then they become more intrusive to install because they're bigger lumps of metal, and ultimately they're very cost prohibitive as well. So track design is extremely important, but it is a balancing act that big guys have to do. Good track maintenance, obviously very key, because as we pointed out, you might have a much higher risk factor if your track's in good working order and there's not as many detractors. And a good use of CRT, we sort of spoke about it earlier, understanding what that's set at, what the actions are that sit behind that. And then remote monitoring, it's a growing tool. And, you know, maybe not as much to mitigate, but to add to that knowledge and add to a live reading of what exactly is going on. Which means it leads me on nicely to the next part about the role in which monitoring can play in this particular track defect. So when specifically looking at buckles and kins, which are caused by the increase in stress, which in turn caused by the increased temperature, if the potential critical relative temperature is different for different climates and localized within those climates, and they're local to the track conditions in the surrounding work, then the first port of call is to understand the temperature of the rail itself, right? You know, forecasting plays a vital role in any rail authority in predicting when they're at risk, especially over the summer months for the northern or southern hemisphere. But confirmation of that track temperature needs to be done to initiate sort of the next steps to confirm that the rail is actually at that temperature. And on the left-hand side is you know, a very manual way of doing it. You put actual thermometers onto the rail to understand. And on the right-hand side is Senceive, you know, version of remote monitoring, where we put a sensor actually on the web of the rail that talks to a wireless node. And to put that sensor into the context of our ecosystem, the sensor is located onto the web of the rail, so it's taking the measurement of the temperature. This can be every minute to every hour, depending on what you set it to. It talks wirelessly to autonomously stored gateway, which then sends its data via cellular network to our cloud base, and then displayed on the front end platform where it can be reviewed, interpreted, or alarmed. It can also be simultaneously integrated with another platform if required. And you can see on the left-hand side, so that's a bit of a small picture, but you see on the left-hand side, you've got the node at the track level, taking the temperature samples. On the left-hand side, you've got the gateway in the distance that's picking up data from that node and sending it to the back end. And bottom right-hand side, you've got sort of an example of a graph showing sort of variation in temperature of the node that we've got on the test side. Measuring the temperature is only half the challenge. As I said, it's certainly a real positive impact on confirming a rail temperature versus a forecast or ambient temperature. It allows the track engineer to compare against the CRT that they've set for a particular track. But it's not actually giving any information on whether there's been a buckle or a kink. You know, we set the CRT based on a lot of criteria, and in reality, some of those criteria are best estimates or best practice. And understanding that relationship, it carries a lot of value, don't get me wrong, and there are buckles that are directly related to temperature, but actually understanding whether a buckle has occurred post that exceedance is the obvious next step. At the moment, quite a lot of reactions from rail authorities worldwide is, okay, we know that the air temperature is likely to cause higher rail temperatures. Right now, we've confirmed that the rail temperature has now exceeded the design factor. They will then, if they can, have to send a watchman out to actually look for buckles within the track. And the next step of our mission is to actually try and capture those buckles through remote monitoring as well. So we want to understand whether those elevated temperatures above that critical rail temperature have in fact created that buckle. And to do this, we place what we call an optical displacement sensor. We place it off track on a stable position, and we shoot directly onto the web of the rail. And this provides a millimeter output, and again take readings anywhere from 1 minute to 1 hour. And the sensor can take those static readings or be triggered by the sensors within the network, such as a temperature sensor. So what we aim to do is provide a complete picture where we provide, and this is, we don't have to go through everything, but we go through the precursor of providing a weather station should you want that, something similar to pick up ambient temperature. We pick up the cause, which is the rising temperature on the track, by placing a sensor on track. We place an ODS to pick up the buckle, which is installed at 90 degrees to the track, pointing at the web of the rail, picking up change in lateral slew. So you can immediately say, right, we've got an elevated temperature, we've got an elevated temperature on the rail, and now we've got millimeter movement in perpendicular to the track, so we start to see that the track is moving. And then we've also got a camera that can validate the readings. And when we say validate the readings, I'll talk about this in a little bit more detail later on, but to also validate the conditions that are on site. As we sort of mentioned in the previous slide, it's not just temperature that can contribute to the buckle occurring. It's the shoulder, it's surrounding works, it's other things as well. And the key element of this whole system is our wireless network and the intelligence that we can sit on top of it, which we call InfoGut. The system can tick along, taking hourly readings, providing nice trends and patterns during cooler conditions or over at night. So the temperature is taking a reading, the ODS is also taking a reading and saying I'm sitting at 0 millimeter movements. And then as the temperature rises, the sensor will also ask the other sensors within its network to say, actually, I'm starting to understand, I'm starting to feel an increase in temperature. I think we should up our sampling rate automatically and go suddenly from half an hour to 10 minutes. And then once it goes past possibly a CRT value, let's say you set that at 35 degrees Celsius, it starts going, hang on, we're now in danger zone. We need to be taking samples every 30 seconds or even 1 minute to make sure that we capture any movement before a train potentially can come over. And it's sending that data directly to our cloud. It's also asking the camera to take images throughout this period to validate anything that's going on. And it means that if something was going to happen, the system will automatically adjust to what's going on and send that information to the back end of the alert via text and emails of what's going on. And the ODS is, it's used is a very simple distance measurement. It measures it from that set point to the welded rail. Its output is in a very simple millimeter format, so it's very easy for anyone to pick up and understand what's going on. But this isn't something we just sort of come up with. It's been something we use globally. It's a way of picking up buckles and lateral slew. We work very closely with Network Rail here in the UK to hone and prove this system works. We recently, as part of a sponsored testing program, part of the project, we invited to try some of our system on a test rig that was built, and it was calibrated to sort of millimeter movements. It was moved by a centrally located hydraulic jack. You can see it in the middle there. And we set up 3 different ODSs. 2 you can see on shot, one on the A-frame, one on the middle section, and one just off track to the right-hand side, that were pointed 90 degrees onto the track and measuring change. We've got a camera in the near ground, looking along the cess, as it were, to validate any movement that we saw. And then what we did is we moved the rig to move the track laterally by 10 millimeter increments. Between each 10 millimeter movement, it would come back to 0. So it would go from 0 to 10, back to 0, 0 to 20, back to 10. And these are the results you can see, and they're extremely impressive. You've got the first 2 were almost, well, within a millimeter each time of the movement. The A-frame, it's not out at all. It's just monitoring a different part of the track, so the amplitude is slightly less, but it's clearly showing 10 mil movement, 10 mil increment. So yeah, it proved that the system worked exceptionally well, and it's a very reliable way of measuring lateral slew. The camera, was triggered, took shots as the movement was happening. And yeah, I'm not going to pretend that the camera can pick up millimeter movement. We're there to validate. We've got to about 40, 50 mil, and you can start to see the bend in the track. But as I said, it's not just there for that, it's there to validate the surrounding environment and see if there's anything else that the track engineer might want to see to understand better the movement that the sensors and the temperature range are showing. So there's still a lot of unsolved challenges that we have. And do we think we have the complete system? No, I think there's still a lot of work to do. Buckles can happen over long wavelengths, and being able to understand the length and the size is a really useful tool. Equally, our current application measures a point along the rail, so assumes a level of understanding of where the buckle might happen. In reality, the buckle might happen over many meters, a section of track, and so you can install obviously multiple sensors, but then it starts to become cost prohibitive potentially. So we've got some work to do on that and how we can improve that. Amplitude, what kind of amplitude is expected, and therefore what's the critical level of movement that you want to be able to capture. Our camera doesn't aim to replace any particular part, but it can support watching you. It has to look along the line of track movement. It can't look directly over the rail like it is in practice, but it can look along the cess. And we've done some testing to show that, up to about 40-50 mil, you start to see some buckle over the smaller wavelengths. Different parts of the rail have different behaviours. Whether you're on a bend, whether you're on a straight, whether you're on points. Understanding those is different, and the setup and the application of the system is different. And so we need to adapt and develop our systems to be able to capture those different environments. Bends are typically some points where people are very nervous about, because you've got a lot of stress on the outside rail. So we've got to understand how our system works in the same premise, but whether it can be developed further to allow better understanding. And installation speed, our systems are all autonomous. They work on battery life. They're solar panel. They can be installed quickly and easily. It's one of our USPs. because we want to make things easy for people. We want them to be able to commission quickly and start getting useful and meaningful data out of them. And when we look at, especially when you're doing activities in the summer, and you're potentially disturbing the track ballast or weakening the track, you're mandated to put some critical rail temperature monitoring to understand what you're doing, onto the track, because as we spoke about previously in the webinar, that's where you're starting to see a decrease in critical rail temperature. So it might be at a higher level. Suddenly you start doing some piling work next to it, and actually the level might be 40 degrees, so you have to do the CR2 next to it. So you need to put something on quickly and easily that's giving you an output that can measure that reliably straight away. So we use the ODS as its installation output. Commissioning time is very simple and clear to the end user. But there are different sensor types that could potentially provide a more comprehensive understanding of that stress change. The obvious thought sort of goes to strain gauges, but understanding and interpreting the data is actually quite tricky. You have to fit quite a few on to actually make sure that you're getting a good average. It's quite intrusive to install, and you need some background time to iron out things like trains that are moving past and other movements. So we're still sort of trying other ways of picking up that movement, but the ODS is a favourite within our client base because it outputs in that format. And the camera, like I said, currently used for just general verification of what's going on site. And so that any changes in rail or the ballast and any mitigating info might be garnished from the imagery. As we said in earlier slides, there's lots of contributors, but we're also working towards pulling quantitative data from the camera, as well as using post-processing techniques, so we can actually start overlaying some of the images as well. These are the two images I've just put on the screen here that from the same spot, but 24 hours apart. We can start pulling some metrics off of those, and suddenly pick up a lot longer range in a very unobtrusive manner. Ultimately, we need to work very closely with lots of the different rail authorities around the world to help solve the growing issues within track engineering with climate change. I don't believe there's one uniform plug-and-play answer that meets all of the requirements at the moment in terms of output, in terms of cost, in terms of practicality, in terms of range, type of track, etc., etc. However, there is a growing improvement in the ability to measure buckle and measure buckle accurately. There's a growing desire to provide more information and detail on this. So at the very least, we can and do provide track buckle and lateral slew monitoring techniques right now for high-risk sites. We need to develop it further and develop some more techniques, but we're on the right path. So yeah, thank you for listening and giving up your time. We should, I think, have enough time for some questions, Jackie.
Thank you, Dom. That was great. Yes, we do have a few questions that came in. The first one is on length of track. The question is, for what length of track can a single ODS sensor detect a buckle?
Yeah, that depends on the assessment of that track, really, I suppose. The wavelength, something I touched on in the last couple of slides, really. The ODS only measures one point, it's measuring directly perpendicular onto the track. And so if you've got a wavelength, a predicted wavelength of the track that can go out of, it's only going to be over 2 or 3 meters, and you've got to know where that is, and that's not always the case. You might say, I've got a mile-long piece of track that's vulnerable. If it reaches this temperature, I could get a buckle anywhere along that track, and you're going to have to place multiple ODSs along that track. Again, it's why there isn't a uniform method, because every track's different, and the maintenance regime, ballast, shoulder, and things like that all play into that.
Thank you. Okay, the next is about output that you mentioned. I think you touched on this a bit, but maybe you could expand. So you said output in relation to measuring the track buckle. Can you just expand on that? That's the question.
Yeah, so I mean, it's obviously, a lot of what I spoke about at the beginning, and a lot of the changes is in stress levels of the railway. So your automatic thought is, why are we not looking at the stress within the rail and changes within the stress? But there's lots of things that impact stress on a daily basis, not just the diurnal movement, the temperature, the type of trains running past it. Especially if you look at here in the UK, we peak hours where we run certain trains at certain frequencies. If you have a track team working, there's lots of impacts that can change that stress level. So you've got to iron all of that out. You've got to understand what normal looks like under those conditions, so that you can then apply thresholds for what out of the ordinary looks like. And it's not impossible at all, but it's time. You don't get as much time. You have to understand. You have to give yourself as much background reading to understand that. And so the reason why I say the ODS is quite a useful tool, and some of the rail authorities worked with SNCF and DB lump for the ODS, will like the ODS, because it outputs literally telling you in millimeter fashion how the track is moving laterally, which is, that's the output of a change in stress, but it's the part that they can then put, hang their hat on and say, right, okay, we know that it's moved. And so it's really about what's meaningful to the end user and easiest to commission.
Thank you. Okay, so at the end you spoke about the challenges. Someone has asked, what improvements do you, specifically Senceive, want to make?
I think, it's twofold really, I suppose. We're always on the lookout for new sensors that we can integrate into our system. We can have that layer of intelligence of infrared on top, which means we can control the speed at which things are sampled. We can control the things at which they're escalated and sent up the chain. So you can be confident that you get your alert when it, once it happens on site within minutes. So we're always going to look out for new sensors that can, expand how we measure track buckle. But one of the big key options we're looking at is how we can use the camera in more detail. How can we, if we put the images on site, and so if we can get good images and we can get good length of tracking within the image, we can get up to 50 meters in night and day in our images. And day, night is less, you don't get many heat waves at night, but we get the images over the course of 24-hour period. We start overlaying those images and we start pulling out metrics for how the track might be behaving. That could be a really neat option going forward for picking up lateral slew.
Wonderful. The last question is this problem of track buckle going to get worse over time? So this is for you to predict, I guess.
Yeah, I know climate change is a bit of a buzzword, so that if you believe everything you read, then we are going to get higher temperatures. We've gone up 1 degree, I think it is, in the last 25 years or something. So we are going to get increased temperatures. When I look at railways around Europe, especially, and some in the US, it's more so the age of the track. When we look at a new track slab, it's much better equipped to take those higher stresses. So it does go to, it gets that big expansion. There's lots of pressure on it. It's been engineered to be able to contain and hold that. It's when we get the older tracks where they've got timber sleepers, they've got points, they've got a big bend, the shoulders starting to degrade. There's some works going on next to it. Those sort of environments are becoming more and more common, really, I suppose, and that's the risk we see, and the problem getting worse every time. In my view, obviously accompanied with climate change, but together it's a pretty lethal combat.
We had one more question sneak in. Have you experienced a relationship between the ODS, the slew, versus the displacement of the ballast or sleeper movement?
Yes, we don't. Part of the challenge is finding a stable point for the ODS to be mounted. So we lots of furniture to pick from. We use OLEs, we use retaining walls, we use our own ballast baskets, sort of gabion basket styles that can be dumped on the side of the track and nice and stable. Things like embankments become a bit harder because you're obviously sloping away from the track, so finding a stable point to mount on. So we don't actually mount on the end of the sleeper of the rail we're monitoring, because the sleeper can obviously move with it, and then you're not picking up any movement. So we've also mounted on stakes as well. So there's lots of options, and that's part of the challenge with any system. It's trying to adapt it. Sort of touched on that in the last couple of slides. Is trying to adapt it with different environments that we have within the track arena.
Great, thank you. I think that was it for the questions. So if anyone does think of any additional questions or wants to reach out, you can always email info.senceive.com, and one of our experts will get right back to you. Thank you so much, Dom, for your time. And you can look out for our webinar for April, and we'll be announcing that in a few weeks. Thank you so much, everyone, for joining.